In this video, we are going to learn about factors affecting rate of reaction. At the end of the lesson, students should be able to A. Explain the effect of the following factor on the reaction rate. 1. Concentration or pressure. 2. Temperature. 3. Catalyst. 4. Particle size. B. Explain the effect of temperature on reaction rate using Maxwell-Boltzmann distribution curve. And C. Explain the effect of catalyst on activation energy using an energy profile diagram. In general, reaction rates generally increase as the concentrations of the reactants are increased. Reaction rates generally increase rapidly as the temperature is increased. Catalysts speed up reactions. And last but not least, the rate increases as the smaller the size of reacting particles. The first factor is concentration of reactants. Reaction rate is directly proportional to collision over time, which means the frequency of collision increases with the concentration. Consider a 4-particle system where there is 2 moles of reactant A and 2 moles of reactant B. These two reactants will collide with each other and produce 4 collisions. When concentration of reactants increases, the frequency of collisions increases. This is described as collision theory. This will also result in the increase in the quantity of effective collision. Thus, the reaction rate increases. Before this, we see the 4-particle system. Look at the 5-particle system, where there is 3 moles of reactant A and 2 moles of reactant B. When these reactants collide, it will produce 6 collisions, which means the greater the number of particles, the greater the number of collisions, and consequently, the greater the number of effective collisions. This observation correlates with the rate law that has been previously discussed. Reaction rate equal K concentration A to the power of X, concentration B to the power of Y. Based on this equation, reaction rate is directly proportional to the concentration of reactants. Please be reminded that only in zero-order reaction, the rate of reaction is not dependent upon the concentration of the reactants. Point to remember: if the concentration is increased, the number of collisions will also increase. More molecules will collide, thus increasing the number of effective collisions. Consequently, the rate of reaction increases. Pressure is also related to concentration and volume. By decreasing the volume available, you are increasing the concentration of molecules in a specific space. You should also remember that changing the pressure of a system only works well for gases. Generally, reaction rates for solids and liquids remain unaffected by increases in pressure. The second factor is temperature. As temperature increases, kinetic energy of molecules increases, so more collisions occur in a given time. The higher the kinetic energy, the higher the energy of the effective collisions. So, more molecules will have energy greater than activation energy. Thus, the rate of reaction increases. The point is, the higher the temperature, the number of molecules possessing higher kinetic energy will increase. More molecules would possess energy higher than the activation energy. Thus, rate of reaction increases. We can describe this using Maxwell-Boltzmann distribution curve. It was easy to draw. First, you draw the y-axis and the x-axis. The y-axis is labeled fraction of molecules having a certain kinetic energy. The x-axis is labeled kinetic energy. Then you draw a sharp curve, the blue one, and label T1. Then you draw a wider curve, the red one, and label T2. Note that the temperature of T2 is greater than T1. Then on the right side, you draw a dotted line to represent activation energy. Then you compare. Like shown in the video, the area ABCD is the fraction of collisions that have energy greater than activation energy for temperature T1. But for temperature T2, the area ABFE is the fraction of collisions that have energy greater than activation energy. You can see that the area for T2 is larger than the area for T1. This means that more molecules have greater energy than activation energy at temperature T2, which is the higher temperature than T1. This distribution curve is called Maxwell-Boltzmann distribution curve. The third factor is catalyst. A catalyst is a substance that increases the rate of a chemical reaction without itself being consumed. Addition of a catalyst increases the reaction rate by increasing the frequency of effective collision, that is, by provide alternative pathway with lower activation energy and correct orientation. Addition of a catalyst changes the value of K. Consider reaction rate equal to K concentration A to the power of X concentration of B to the power of Y. The changes in temperature. The addition of catalysts will change the value of K. We can see the effect of catalysts in the following energy diagram for an exothermic reaction. The reaction is faster when a catalyst is used because the catalyst provide alternative pathway with lower activation energy. If there is no catalyst, the reaction will take a longer pathway and the activation energy is higher. This is how you draw an energy profile diagram to compare the reaction with catalyst and without catalyst. Keep in mind that the function of catalyst is not to lower the activation energy, but it provides an alternative pathway for the reaction with a lower activation energy. Last but not least, the fourth factor, particle size. The smaller the size of reacting particles, the greater is the total surface area exposed for reaction, and consequently, the faster the reaction. In simple words, the smaller the size of reacting particles, the higher the rate of reactions. That's all for factors affecting reaction rate. Thank you.